Welcome to the Avid Technology Podcast with me, Ryan Morn. Today's podcast, we have got Dr. James Goss from Motor Design joining us. He is an expert in motor design, and Motor Design is a company of, I think, the leading manufacturer, developer of design software for electrical machine design, particularly in the high-performance automotive space. So James is an absolute wealth of information on machine design and development and software tools, and also, he's kind of seeing what's happening in the industry before the industry seeing what's happening in the industry. So it's really exciting to get James on the show. So it's great to have James Goss here today from Motor Design to talk to us about his background and career and about the really fascinating work they do at MDL. So thanks for joining us today, James.
Great. Thank you, Ryan.
Could you just start off by telling us about yourself and a bit about your background and where you're from?
Yeah, no problem. So I'm obviously from the UK. I grew up in Hampshire and the South Coast. And I guess I started my engineering education with a systems engineering degree at the University of Warwick. It was kind of a general engineering degree, but with a kind of a focus on the electrical engineering and some of the programming and computer side of things as well.
Okay.
And then after that, I went straight into an engineering doctorate at the University of Bristol. So I came out of my undergraduate and I looked at, lots of different options, but there seemed to be limited career options at the time. It was sort of going right in the middle of the financial crash, and the only sort of obvious path for a graduate engineer was in the defense industry, and it wasn't something that really motivated me. So I took up this engineering doctorate at the University of Bristol, and that was quite generally defined, but it was to do with the design of electric motors for electric vehicle applications.
Oh, right. And was that something that had been of interest to you before that point?
It had a little bit, I guess, but actually I think at the time I was more focused on renewable energy, and that was the thing I wanted to do. But I saw this opportunity and thought, well, that sounds interesting. At the time it was about 10 years ago, so 2009, and not many people were taking electric vehicles particularly seriously. It was really pre Tesla.
Yep. Milk float jokes all around. Lots of jokes about milk floats and things like that.
Exactly. I think like the classic electric vehicle was the Mitsubishi iMEV. Nobody thought this was something that was they were going to be driving in anytime soon. Yeah. But I thought it sounded interesting, and I went for this sort of opportunity.
Oh, wow. And that led you to Bristol. And an engineering doctorate, they were quite big for a while, weren't they, the EngDs? Don't so much do them anymore, I don't think.
Yeah, so the idea with an engineering doctorate was that you would have an industry sponsorship from a company, and you would spend some time in the university and sometimes some time in the company, and your work would be on that boundary between industry and academia.
Ah, okay. So who was your industrial sponsor in that case?
So the industrial sponsor was Motor Design Ltd. So it's the same company that I work for now. At the time, it was a lot smaller. So there was only, I think, 3 full-time employees at the company at the time. Wow.
So quite a big jump then for you in terms of you're looking at your future career. Not only are you stepping into something which is far from a certainty in the marketplace, but you're doing it with a very, very small company. Did you see that as being a big risk, or was it something that excited you, or did you just not think about it?
I did, to be honest. I didn't think about it too much, really. I was just interested in the technology and the engineering, and it was an early stage in your career, so I guess you don't think of it as much of a risk. You're just exploring things and knowing you can go somewhere else if it doesn't work out, but thankfully it seems to have done. So, yeah.
You're doing it. That's pretty good in terms of starting life as an eng doc with the company, and you're now the CEO.
Yeah,
it's a pretty good career progression.
Yeah, so I guess I can explain a little bit about how that happened.
Yeah.
Maybe it's worth talking firstly about what the company does, just to give people a bit of background so they can kind of understand,
Yeah.
things. So, yeah, so Motor Design Limited are a company that specialize in the design and the simulation of electric motors. And the main business is the development of a software tool that's used for the design of electric motors. So it's called MotorCAD. Basically, engineers and companies use this software tool to input designs and do simulations and predict, how the design is going to perform. And that could be how hot it's going to get, how much torque or power it's going to produce, and even some of the mechanical behaviors. How much stress is there going to be on the laminations, or how efficient the motor is going to be over a drive cycle or something. That's effectively what we do, is we develop this software product and sell it to engineering companies such as automotive OEMs like Jaguar Land Rover, or tier one suppliers, I guess, like yourself, Avid, or people like Bosch as well. And so my task when I was sort of started the engineering doctorate was to take what were the cutting edge at the time, the simulation tools, and try to design an electric motor for an EV application, a pure electric, battery electric vehicle operation. And I guess what I found is that these tools were not at all designed for this, and they were actually, really focused on industrial motors, which tend to operate, pumps and fans, and they operate at constant speed with much simpler control. And it was actually a real challenge trying to do a design of a motor using these tools.
Yeah.
So that kind of gave me a natural progression into changing them, developing them, and putting new methods in and developing new techniques to simulate and design electric motors, but with a focus on the electric vehicle automotive applications.
And I hadn't quite realized that was so MotorCAD as a product had existed at that point, but was more focused on kind of industrial applications.
Yeah, I guess the whole sort of electric machine simulation industry was kind of focused on these industrial applications, because that's the history of electric machine simulation. And, really there was very few people trying to do the electric vehicle propulsion traction motor designs. So the tools hadn't been developed in that way. Right.
And you kind of learned and developed all of that, the improvements through your engineering doctorate. Were they big challenges, to overcome? I guess in some ways there were. I mean, we obviously have a team here. It wasn't all just me doing this. There was a team, and experts from all different areas contributing to develop this product. So yeah, there was lots of challenges as you go along the way. But that's part of the fun of engineering, I guess, isn't it? Yeah, we kind of see this now. It's something that is not very well understood. The difference between the kind of low performance industrial motors and then what we're trying to do with these very, very highly stressed, high performance, super cost optimized machines for automotive. I do find a lot of people don't kind of recognize. I mean, it's almost an entirely different engineering discipline, and people find it really quite hard to go from one to the other. Some people manage. But particularly in the automotive side, because it's such a new thing, there aren't loads of people out there who've been doing it for the last 20 years, because it didn't exist 20 years ago. Yeah, no, definitely. And, in some ways it's a different language as well. Some of the things that you're talking, particularly on the control side as well, how the machines are controlled and operated. You need to understand that really to do the design properly. So yeah, we do have this, but I mean, a lot of the electric machine designers we work with are historically sort of industrial machine designers, and they've developed further and started to look at some of these higher performance applications. So the principles are the same. It's just that you're pushing things a lot harder now, and that's also where the simulation tools come in, because you really need to design to the limits of performance. Right. And in the last 10 years, MDL has grown massively as a result of this. Do you want to just kind of fill in the gap in terms of where you guys are now as a business?
Yeah, so, well, I guess once I came out of the doctorate and I started working full-time at MDL, one of the first projects that I was involved in and was working with was a collaborative project with Jaguar Land Rover. And this was, it was producing a range of different prototype vehicles, but the flagship one was this full electric Range Rover Evoque. So it was a quite familiar setup actually. If you look back now, where you've got electric motor on each axle, and the kind of the battery under the floor, this kind of skateboard structure. But that was at the time, a project that was quite exciting and fun to be involved in. And obviously a lot of the tools are developed on that, and that kind of set us on that path as well. And that project, actually, many of the elements of that were taken into the I-Pace.
Wow!
So it was really the start of JLR, doing this full battery electric vehicle project.
So when about was that with an electric Evoque?
Yeah, so I'm trying to remember exactly. I mean, it was around 2012, I guess. Wow. 2013, something like that.
So not something that many people would even have known that they were working on at the time, I guess.
Yeah, well, it was just a prototype vehicle, I guess, to see what could be possible. But it was, very interesting research and really, really good to be involved in that, and gave me a really good insight as well as to, we develop the tools here, but to actually apply them on a real project in an actual design environment, and then have to develop a vehicle. It gave you a really good insight into how that happens and what the sort of needs and requirements are. So we've kind of taken that and really pushed forward and developed those tools. And MotorCAD, has got a lot more functionality and capability than back, when we started doing this. Yeah. I'd say now probably the majority of automotive OEMs and tier ones are using our software tools in some way to design the next generation of hybrid electric vehicles. So the company, I think I mentioned, there was about 3 full-time employees in 2009 or when I started, 3 or 4, and now we're up to over 30. But that's not where it's going to stop, and we keep growing very quickly.
No, that's a pretty fantastic success story, really, to go from a couple of people, because you're based in the northwest of England.
Yes, so we're based in Wrexham, so it's actually just in Wales.
Okay, so in Wales, known for being a hotbed of software development activity. Yeah, an amazing success story in terms of now, and it certainly, I mean, everyone that we work with knows your product. I haven't come across anyone who doesn't use it. And normally this kind of thing is the territory of the mega corporations, your kind of Siemenses and that kind of thing. But it really is a small British company. You've managed to carve out a massive, very successful niche for yourselves.
Yeah. No, I think, obviously we do have competition from companies like Siemens and Altair. But we really focus on the application, which is the electric machine design and being experts in the design and simulation of electric machines. Whereas I think a lot of these other sort of larger software companies are more focused on physics and generating tools that cross different physical domains. So they have electromagnetic solvers, CFD thermal solvers, and there'll be general tools that you can model sort of any electromechanical or electromagnetic device, whereas we are a very specific, dedicated tool for the design of electric motors.
So the right product at the right time for an industry that was about to boom.
Yeah, exactly. Yeah.
All, of course, judgment and good planning on your part.
Yeah, a little bit of luck maybe as well.
No, yeah. I don't believe it.
Yeah.
Premeditated. So what kind of things are you guys doing now at Motor Design? Where do you mainly concentrate on software development, or because you still do quite a bit of consulting work as well, don't you, in terms of machine development?
Yeah, and research as well. So, we're always trying to push the boundaries for electric motor design. So developing, I guess, new techniques for simulating and designing the machines. We do consultancy projects. So people come to us with design specifications and we develop designs to those specifications or explore different design configurations for them or compare different choices. And then obviously, continuous development of the software. The more users we get, the more and more requirements we have for new bits of functionality and new things to build into the software. So it just gets busier and there's more things to do.
Right. Are you mainly, would you say, a software business now, or mainly?
I'd say mainly, yeah. I mean, the consultancy is very important, and we've got a really good team of electric machine experts here who work on the consultancy. But the main core of our business is the software development, definitely.
Right. And that must give you a really a good kind of insight and reach into what is happening at the moment with electrification being one of the key tools that companies are using. I guess you would get a real sense for who is working on electrification, where teams are growing, where the effort is going in, and all the kind of interesting stuff that's happening at the moment.
Yeah, I mean, you do get a general sense. I mean, obviously, there's a limited amount that companies want to share with you. But yeah, you do get a good sense of the effort and the growth and the interest in certain areas and particular technologies.
Are there any key sort of observations that you've got about where the market is at the moment from what you see?
Yeah, I guess so. I mean, we're constantly being asked to look at new electric vehicle powertrain concepts and different things. I guess we're seeing a move to more integrated electric drive units. So this is where the motor, the power electronics, and the gearbox are all combined into a single unit.
Right.
Whereas maybe previously it was more, you deliver a motor, you deliver a separate box that does the electronics, and you've got a gearbox that's coupled to it. So now we're seeing more of an integration and also more sort of a design of that electric drive unit as a whole. Right. And trying to sort of make design decisions that maximize the performance of that or the size of that or the efficiency of that unit as a whole, rather than just making individual choices at the component levels.
Oh, right. And are you having to bring functionality for some of those other elements into your software, or are you how are you handling that?
There's a mixture, I guess, between building things in and coupling to other people's tools as well. So whether it's the gearbox or the power electronics, obviously our expertise is always in the motor, but to be able to bring in some aspects of those other elements or couple to other tools that do that allows you to kind of do that integrated design.
Wow. Does that mean, are you having to get involved in partnering with other software companies, or is it more of just making sure that you can pass data from product to product?
Yeah, a bit of both. And I think a recent development is people looking at the sort of system simulation standards. And there's some nice sort of standard interfaces which have been defined, and that really helps because it means that everybody can work to one standard interface and then couple different models together.
Okay, so just that's completely new to me. Just tell me a little bit more about that. And when you say system, you mean as in modeling software system? Yeah. Okay.
So I guess there's lots of system simulation tools, things like Simulink, which is part of MATLAB or MathWorks, or GT Suite or AmaSim, and these are all system simulators. Yeah. And what you want to be able to do is take individual models from different components and connect them together. And there's a standard. I mean, it's called a functional mock-up interface or a functional mock-up unit, and that really defines what the input-output characteristics are. So it means I can plug my motor model into that. And somebody else who's got maybe a gearbox model or a power electronics model or a vehicle thermal cooling system model, and can connect these together in a seamless way without having to develop custom linkages between these different supplied models.
I guess that probably highlights people really starting to think at a systems level in a much more sort of smart way about maximizing the performance of the whole system rather than kind of discrete component engineering concentrating on the individual devices. Does that sound?
Yeah. So I could give maybe a very simple example. Is if you take the electric motor and you want to make it as power dense as possible. So that's the smallest size for the most amount of power. You make it a high speed motor. So motors are sized on their torque output, not on their power output. So and as power is your torque times your speed. If you increase the speed and lower the torque, you can have a smaller motor for the same output power. That reduces the weight, reduces the packaging size, and it's all good. However, that power has to be transferred to the wheels via a gearbox, and the bigger the difference in the speed of my motor shaft and the wheel, the higher my gear ratio needs to be, and the larger the gearbox is. So, what is the right number there? What's the right speed to choose that makes the motor small but doesn't create such a large or complicated gearbox? And that's kind of a simple example of one of those systems levels trade-offs that you've got to try and make. And the only way of answering that is by doing detailed simulation at the concept level, and being able to decide, well, if I was to make the motor, this much faster with this much lower torque requirement, how much smaller does it get compared to how much bigger does the gearbox get? Yeah,
we experience that quite a lot. It's a huge topic, actually. Big area. What do you think in terms of, a lot of people say with a combustion engine product, there's a huge variation. The engineering in the engine is massive, so therefore, a difference between an Audi brand values and performance attributes and Jaguar Land Rover, it's huge, and kind of the engine defines the product. Whereas for e-machines, I've heard some people say, well, the e-machine, it's kind of, they're going to become standard. An electric motor, there's not all that much that can differentiate between them, and therefore we'll end up homing in on standards. And then other people say, no, e-machines and electronics in the system, there's such a huge, it's much more subtle and complex than that, and you can't do it that way. Do you see a kind of trend of more heading towards standardization or more divergence in terms of different performance requirements and machine types and system topologies? Which way do you see it going?
Well, I think, I have heard that various times in the past. I think what you've started to see when some of these major brands have brought out electric vehicles onto the market is actually that's not really the case, and there is a huge difference between the drive cycle efficiency of a Tesla Model 3, the Hyundai Kona, the Audi e-tron, and the Jaguar I-Pace, and they've all got a different balance of aerodynamics and motor technologies, and four-wheel drive versus two-wheel drive. But there's definitely big differences there, and they're competing on those attributes. So, and those attributes are again absolutely clearly driving purchasing decisions by consumers. So I don't think that's the case. I think there's lots of interesting things you can do with motors as well in powertrain configurations, in terms of performance characteristics, torque vectoring, four-wheel drive. I don't know if it's going to be as strong as the internal combustion engine and the brand differentiation, but I think it's always still going to be there.
Cool. Yeah, you mentioned something quite interesting there in terms of the manufacturers that have got product on the market at the moment. There's a huge range of efficiencies, and it's actually something that some of the more established brands, I won't pick one because you can basically say it applies almost universally, have been getting a bit of a hard time about recently. I know everyone obviously does the Tesla comparison, but then so Hyundai are doing exceptionally well with efficiency at the moment, and Tesla is obviously the benchmark for larger vehicles. What's your take on that? Why do you think that the established OEMs are such a long way away? I mean, you sort of 30-ish% difference in efficiency between a Model S and some of the competitor products. What do you think is driving that? Is it as simple as good motor technology, or are there other characteristics?
Yeah,
of
I
the
guess
powertrain?
it's motor technology choices as well. I think one of the things that we see in the four-wheel drive vehicles is you've got a motor on each axle.
Yeah.
And in terms of efficiency, a lot of the time, normal typical driving, say motorway cruising, you're only really needing the torque from one of those motors. The other one is effectively redundant in terms of the difference between the sort of cruising case and the torque required for that versus the full output is quite different. So if you use permanent magnet motors for both of those, then they're constantly excited, and that means that even when they're not outputting any torque, but they are rotating, you're generating losses in the machine due to the changing magnetic field, inducing eddy currents in the conductive components such as the electric steel laminations.
Yeah.
What you find with the Tesla is when they go to the four-wheel drive configuration, they actually use two different motor technologies. They use a permanent magnet motor on one of the axles, I can't remember which one, and an induction machine on the other. And the induction machine is quite different to the permanent magnet machine in that the field on the rotor is induced during operation, but if you're not exciting the winding, there is no rotor field, and you don't have really hardly any no load losses. So that's sort of one example, I guess, of how you can make those different decisions, and you will end up with different efficiency characteristics. Yeah,
it's interesting. Yeah, the freewheeling, people have tried clutching motors out when they're not needed. I mean, in some ways, if you're splitting the power between two machines, you're kind of dividing the current, and maybe you might be more efficient. But I guess in the very lightly loaded conditions, then the problems these cars have they're overmotored.
Yeah, well, if you take an efficiency map of a permanent magnet machine, I guess if you look at the sort of medium to high speed and quite low torque, the efficiencies just won't be very good there. And actually, you want to move up a bit. You want to move up in the torque range. So by splitting it, you'll end up driving them both down to lower efficiencies.
Yeah.
Which I guess is the same thing. It's just effectively you've got double the no load losses that you would do if you only had one motor.
So in a situation where they're highly loaded, it could be better, but in a situation where they're lightly loaded, it could be worse.
Yes.
Do you think that's why machines with more reluctance are starting to become quite common?
Yes, I mean, I guess most of the permanent magnet machines we see have a significant component of reluctance torque. So, I mean, this reduces the amount of rare earth permanent magnet that you're using, which is always good because it reduces the cost.
Yeah.
As you say, I mean, for these no-load losses, they're going to be lower. The power factors are good with those machines, so you tend to have good inverter utilization. So there's quite a few different reasons, really, why they make sense. And I'd say almost all of the electric vehicles out there have a sort of a permanent magnet machine that uses a significant amount of reluctance torque.
Yeah, we were looking at difference between the Audis and Tesla and the new Taycan. And that actually the Taycan's got a nice motor setup compared to a Model S, with the IPM all round. Like you're saying, it's not always as obvious as the induction machine is less good. But in the new cars, the Model 3, Tesla's gone to an IPM motor at the front and the back with a varying amount of reluctance torque in.
Okay, that's interesting.
It's the Porsche's there, but the Audi then has come to the market with induction machines front and rear. So that's it's just kind of interesting seeing how this is all working out with the different manufacturers and how they're going to get to compete. Do you see any particular trends coming through from your work and the kind of people that you're dealing with? Is there any direction?
What in terms of electric motor technology? Well, I guess another thing I was going to say also is The winding technologies are quite different.
Right,
So
okay.
there's a lot of interest in something called hairpin winding, which is like bars, big conductive bars that are used to wind the machine. And these are good because they have, very low DC resistance. So they have low copper losses, and they're very predictable as well in terms of in a mass manufacturing environment. So when you produce many of these machines, there's little variation in the performance, but they do have some drawbacks, which is at higher speeds, higher frequencies, there's eddy currents induced in those bars, and they generate extra losses as well. So again, we see a bit of a mixture of that, different profiles and different manufacturers. But that's definitely a big trend as well at the moment, is going towards these hairpin style windings.
Much better than the kind of older type was the pull through or the slot insert windings that are externally formed and then kind of dragged into the stator slots. Mm-hmm. Is there much on concentrated sort of segmented stator tooth winding? Is that a viable alternative to hairpins, do you think? Or
well, we see those in applications where there's very limited axial length. So you've got a very, very short machine. A good example is the plug-in hybrids. So where you've got the motor sort of sandwiched between the internal combustion engine and the transmission.
Yeah.
But in the battery electric vehicles where you've got more space there, we don't really see the concentrated windings having a big impact. I guess there are, again, various different reasons for that, but one of the main reasons is that they don't utilize they don't generate anywhere near as much reluctance torque as the sort of distributed windings.
Right.
Which means that you do end up just using more magnet to deliver the same torque. And if you look at a design with a concentrated winding, you'll always see it's got, much less designed for a reluctance-based torque with multiple barriers and magnet layers, and typically it's only one magnet layer with quite a large magnet used.
Oh, right. That's really interesting. So in the BEV space, I mean, it seems like it's there's not particularly a right or wrong answer, but there is an awful lot of design considerations that you would have to take into, or people are taking into account when they're trying to come up with a machine choice. In terms of what people are trying to get, is it taking weight out or cost out of machines or more performance for this? What's the kind of general direction there? Are people focusing on materials optimization or?
Yeah, I think this is one of the challenges we have, is we've got competing objectives. So we want to maximize our efficiency over a drive cycle. We want our machine to be very small, and we want it to be very cheap. And, all of those objectives are conflicting, really.
Yeah.
So I guess a lot of what we're trying to do is allow people to explore the design space, evaluate using simulation all these different design configurations and options and winding types and machine technologies, but be able to evaluate that trade-off. So understand what that trade-off looks like and how much efficiency can I gain if I increase my size a bit, or what's my opportunity to reduce my cost at the expense of my efficiency or something, and allowing designers to be able to explore that space and choose the right balance of those competing objectives for their particular application.
The kind of intuition would be that the battery is really expensive and the motors are much less expensive. So you might sacrifice a bit of motor cost so that I have a more expensive motor if it was going to get you better weight or efficiency to basically help you stretch out your battery performance a bit further. Is that, do you think that's a sort of true statement, or is that kind of... Definitely. And I mean, this is why the majority of electric vehicles on the market are using permanent magnet machines, is they're more efficient. So although the cost is higher, the efficiency, the cost pays for itself in terms of the extra battery capacity that you would need to achieve the same range. But there is many other reasons as well, and many other things that sort of weigh on these decisions, and packaging space is quite important as well. Yeah, and even purchase price, and so there's not one answer really, and there's always a point at which it doesn't make sense anymore. There's always a point at which I can add more cost
to my machine to get more efficiency, but that's a tiny amount of efficiency for a very large increase in cost. So you still need to know what that trade-off is and where the sensible point, what's the optimal point to choose.
The law of diminishing returns.
Exactly, yeah.
So what does, in terms of the future for motor design as a business and for you personally, what does that hold? Where do you see yourselves going in the next couple of years?
Yeah, so, I mean, the market's continuing to develop and grow, really, really quickly. And we're working really hard just to keep up with it, working with our customers and our partners to, push the boundaries of electric motor design. And obviously it's driven a lot by the automotive sector, which we've talked a lot about today, but that's not the only area that we're working in. We're definitely seeing a strong interest in the electrification in the aerospace sector as well. So this is propulsion applications, vertical takeoff, more electrification of aircraft or hybrid aircraft and different things. So I'm sure we're going to end up doing a lot of work in that area in the future as well.
Wow. And that's a huge new market that's emerging. Does MDL get involved much in kind of robotics and that kind of systems, or is that more conventional motor technology?
Yeah, we've had some interest in that, but yeah, again, I think that will come at some point.
Cool. And in terms of just in general now, thinking sort of slightly outside of the company, coming up in the next few years, what are the things that are getting you excited in terms of what is happening around us and what's coming?
I guess we see a lot more development of different vehicles. So I think we're going to see a lot of interesting competition come out soon. So I'm very enthusiastic to see what all of our customers have been working on the past couple of years and when that comes onto market. And as we talked about earlier, I think we're going to see a real mixture of different concepts and different ways of creating differentiation between their offerings. And we're going to end up with some really nice vehicles, I think. From within the company, some of the stuff that we're doing, we starting to do more and more large scale simulation and optimization. So using leveraging the simulation tools to generate, really large data sets, explore that design space, look at thousands and thousands of different design configurations, and understand the system level trade-offs and try to enable engineers to have access to this and understand this data in a way that is not really possible at the moment. Is
that starting to get into the territory of sort of AI and machine learning for adaptive design?
Yeah, I don't know about that necessarily, but definitely, it's a lot of the cutting edge data processing and visualization techniques and how we can use those and leverage those to help us in the design process. But as far as I can see at the moment, the design aspects are always going to be driven by an electric machine designer or an engineer, and the tools and the simulation and any intelligence that the sort of computing can offer will be as an aid to those designers rather than just, doing the whole thing for them. Yeah.
It's a huge, one of the big challenges that we see, and a lot of people that we talk to see, there's a huge shortage of talent, of people, because basically we're in an era of electrification of pretty much everything, and where even light bulbs have got power electronics and embedded software in these days. So the demand for engineers who know about power, who know about machine design, electromagnetics, etc., is really, really high in any number of industries. Ways of kind of getting around that, because it doesn't seem like you can do much to increase the supply quickly, because it's a long process of, right back to kids at school and getting them interested in science and engineering, but ways of kind of simplifying the design process and making it more, so people can achieve more with what they've got, basically team-wise, seems to be quite a big area of opportunity at the moment.
Yeah, and I guess that is a lot of what we do as well. And what's unique about our software tool, we build a lot of our expertise into that. So a lot of the knowledge of how to set certain simulations up or configure things, or how to choose certain parameters is embedded in the software, and that's the expertise sort of built into it. And it's something that you wouldn't get with a sort of a more general physics-based solver. Yeah. So having some of that design expertise in there, and I guess that's part of the reason why we're quite successful in doing what we're doing, is that there's a lot of people who having to adopt and learn electric machine design, and having tools which capture a lot of the sort of existing knowledge in them is very helpful.
Yeah, you could have remember like the old Microsoft Word talking paperclip.
Yeah.
Yeah, you could have you and some of your colleagues kind of popping out the screen, talking heads, giving people advice on their designs. Do you think that's a feature you could accommodate in the software in the future?
Yeah, I think I'll think about it, Ryan. I'll think about it. Yeah.
Brilliant. Well, we've just gone slightly over, so thanks very much for taking the time out today, James, to do this. I really appreciate it.
No problem.
And all the best for the future.
Thank you very much.
Okay, that's all we've got time for today. Thank you very much for taking the time out and listening to this episode. We really appreciate it. We hope it's brought you some value. Don't forget, if you've got any questions or things you'd like to know more about, please feel free to send those to us via the usual channels. You can find those in the show notes below, links through to our website and social media feeds, etc. Please hit like, leave us a rating for the show. It really helps us in terms of the ratings and rankings. Share the show with other people. That also helps us. We're doing quite well at the moment. We're in the top 10 in North America, number 6 in the UK for technology podcasts. So that's awesome. We'd love to keep that up, bring in more value and engineering knowledge to people all about vehicle electrification. So if you could help us do that, I'd really, really appreciate it. Like I said, that's all we've got time for today. So I look forward to speaking to you again soon.